In this lesson, we're going to be talking about measurement and scientific tools. I call these the science toolbox. Many tools are used in science, of course, but what do you think is the most important tool you might use? Spare a guess? I'm hoping you're guessing your brain, because that is what it is. Among other things, your brain allows you to ask questions and make hypotheses. Other science tools allow you to make measurements and collect data. An experiment is also classified as a science tool. Some science tools are big and heavy, kind of like, as an example, a huge telescope, like on the picture that you see there. Some are small, like a ruler that measures distance, or a graduated cylinder to measure volume. So in this lesson, we're going to go into the science toolbox and see what else is in there. Just like in the other lessons that we've talked in detail, you're going to have some key concepts that you need to write down in your science journal. Okay, so I'm going to pull those up here so you can see them. It will be the red bullet point, which the first one is this one. Why did scientists create the International System of Units, or SI? That needs to be written down, as well as the next one. Why is scientific notation a useful tool for scientists? And the third one that I want you to take a look at and write in your science journal would be, how can tools such as graduated cylinders and triple beam balances assist physical scientists? Those three questions are the essential questions that we need to take a look at that will be answered within this lesson. So what I want you to do is write those questions down, and we will talk about them. Once you go through your information, you should be able to answer each one of these. The other thing I need you to remember is that we have some vocabulary words that are kind of important in this lesson. You're going to be writing your vocabulary words down in your science journal. And once we come across them in this lesson, you're going to go ahead and write the definitions next to them. So you'll have description, you'll have explanation, you'll have International System of Units, or SI, you will have scientific notation, and the last one you'll have percent error. Each one of these pieces of information for the vocabulary words will be covered in this lesson. Okay, so at this point, I want you to take a look at another question that I have. I need to probably make this a little smaller and make this a little larger so that you can write this one down in your science journal also. But this is one that you'll be answering presently. Why is it important to include an explanation with your description of something you have tested? Make sure that you're writing this one in your science journal and answering this question. This is something that goes along with the lesson that I need to see what you know, what you think about it. Okay? Remember that you can always pause this to write down any information I've asked you to write down in your science journal, and then you can start it up again as soon as you've done that or made and answered your questions. If you don't understand something, please make sure that you go ahead and replay the information again. And if you still don't understand, feel free to please come to me with those questions that you have in reference to the material so that we can talk about them. Remember that my door is always open for your questions whenever you need me. Okay? So feel free to bring any question. No question is silly, so please bring it to me no matter what kind of question you have. Again, please make sure that you have all of this information written down in your science journal so that we can talk about it in class for our classroom discussion, and so that you have information to study from for your quizzes. Okay, suppose you work for a company that tests cars to see how they perform during accidents, as shown in this picture right here. You might use various scientific tools to measure the acceleration of cars as they crash into other objects. One scientific tool you might use is description. Now, a description is one of our vocabulary words, and I want you to write down the definition. A description is a spoken or written summary of an observation. So something you witness or you observe, you write a written summary, which is called a description. Okay, so suppose we're going back to that example of the testing of the cars during accidents. The measurements you record are descriptions of the results of the crash test. So say later your supervisor may ask you to write a report that interprets the measurements you took during that test. Well, using our next vocabulary word, which is an explanation, I'm going to pull this up here, explanation. Oops. Okay, there we go. An explanation is an interpretation of your observations. As you write your explanation, you make inferences about why the crashes damaged the cars in a specific way. Okay, I want you to notice that there is a difference between a description and an explanation. When you describe something, you report your observations. When you explain something, you interpret your observations. A simple description of an experiment is not complete. There must also be an explanation of the data and the results. Okay, so I want you to make sure that you've written those two definitions down, as well as those vocabulary words. Okay? Next thing I want you to notice, and I'm going to close these two into smaller. I want you to notice the question that I'm going to ask you. Okay? Make sure you're writing this in your science journal and answering this one. The question is, why is it important to include an explanation with your description of something you have tested? Okay, we're going to need that answer, so make sure that if you don't understand some of the things we've talked about, you go back and listen to it again and then answer this question. But this question needs to be answered in your science journal. Okay, closing this down, and let's talk about something else here real quick. Have you ever noticed in class that sometimes I might mention meters instead of feet? Or that we talk about Celsius instead of Fahrenheit? Well, different parts of the world use different systems of measurements. This can cause confusion when people who use different systems communicate their measurements. This confusion was eliminated in 1960 when a new system of measurement was adopted. The International Accepted System of Measurement is International System of Units, or SI. Okay? SI. And I want you to write that down because that also is a vocabulary word. International System of Unit is the Internationally Accepted System of Measurement. Okay, I want you to understand that though the United States uses the English system of measurement, nearly all scientists use the International System of Units, often called the metric system. This is why scientific tools are marked with SI units of measurement. And to go on a little further, scientists developed the SI to standardize units of measurement worldwide and to make communication among scientists consistent. Okay, now we want to talk about base units, which is something that we're going to be using in this class specifically. Okay, when you take measurements during scientific investigations in labs, for me, you're going to be using the SI system and these terms right here. We're going to be talking about meter, kilogram, seconds, Kelvin, ampere. All of these terms are SI base units. The SI system uses standards of measurement called these base units right here. Other units used in the SI system that are not base units are derived from these base units. For example, the liter used to measure volume was derived from the base unit for length. Okay, so now I want you to write down some important questions and answer these from the information that we just seen. Okay? Write it down in your journal. What is the standard unit of mass in the SI system? What is the standard unit of mass in the SI system? The next question, what SI unit would you use to measure the boiling point of a liquid? Okay, make sure you're writing that and answering that question in the science journal. You can use that question, and you can use table 1 that I had up a while ago to answer that question. Your next question will be along those same lines. From which base unit do you think volume was derived? Okay, where did it come from? Where did the term volume come from? All right, those are the 3 questions that I have for you. Okay, so we're going to go on here, and I'm going to move some information around so that you can have this information up, which is the second table. And we want to talk about a different type. Older systems of measurement, usually there was no common factor that related one unit to another, like we talked about with volume and length. The SI system eliminated this problem. Okay? This SI system is based on multiples of 10. Any SI unit can be converted to another by multiplying by a power of 10. Factors of 10 are represented by prefixes as shown here in this table. Okay? For example, the prefix milli, okay, that would be this one right here, M-I-L-L-I. This means 0.001 or 10 to the negative third power. So a milliliter is 0.001 liters, or 1/1000th of a liter. Another way to say this is 1 liter is 1,000 times greater than 1 milliliter. Okay, so let me just throw something out there for you. How can you convert one SI unit to another? You remember that you can multiply or divide it by power of 10. Okay, so each one of these is a change by 10. Okay, divide or multiply. Okay, now I want to talk about converting among SI units. Okay, so let me move some things around here for us and get out the main screen. Okay, and hopefully we can start to understand this information. Okay, this is figure 5. In figure 5, you'll notice right here there's a rock. Okay, it has a mass of 17.5 grams. Convert that measurement to kilograms. Okay, so we know that the mass is 17.5 grams. Okay, we're going to follow the instructions here. Okay, looking at number 1, determine the correct relationship between grams and kilograms. So we know there are 1,000 grams in 1 kilogram. Right here, 1,000 grams in 1 kilogram. Okay, so we want to take 1 kilogram and divide it by 1,000 grams. Okay, you want to do the multiplication. X over 17.5 grams equals 1 kilogram over 1,000 kilograms. Okay, continue to do the math. It's all right here. Okay, 17.5, you're crossing out the grams, okay, times 1 kilogram divided by 1,000, okay, X should equal 0.0175 kilograms, okay. check your units. The unit grams divides in the equation, so the answer is 0.0175 kilograms. Okay, we will go over more of that in class, but I want you to notice the steps that we're listing here. Okay, I know math and science are very confusing for some. Matter of fact, I know for a fact that when I hand out science reading homework, the math problems are usually left blank by many people. So please, this is a different year, and we're going to start doing the math problems because math and science is very important. They go hand in hand. Okay, now we want to talk about measurement and uncertainty. Some of you might be familiar with the terms precision and accuracy. In science, these terms have different meanings. Precision is a description of how similar or close repeated measurements are to each other. Accuracy is a description of how close a measurement is to an accepted value. We're going to use this table right up here. Okay, we're going to use that table to differentiate between precision and accuracy. If you look at the table, students were asked to find the density of sodium chloride, NaCl. In 3 trials, each student measured the volume and the mass of NaCl. Then they calculated the density of each trial and calculated the mean or the average. As you take a look, here's student A, here's student B, and here's student C, 3 students. Student A's measurements are the most precise because they are closest to each other. If you take a look, look how close they are to each other. Okay. Student C's measurements are the most accurate because they are closest to the scientifically accepted value. If you take a look, accepted value right there. So student C's information is the most accurate because it is the closest to that accepted value. Student B's measurements are neither precise nor accurate. They are not close to each other or to the acceptable value. So if you take a look, student B's information is all over the chart. Okay, so they are not accurate and they are not precise. Okay, so now I want to ask you the all-important questions as I've been doing so. Okay, so please write these questions down and answer them in your science journal. What does it mean to say that a measurement is accurate? Okay, the next one. What is the difference between precision and accuracy in measurements? Okay. 2. And the last one. Can measurements in an experiment be accurate but not precise? Those 3 questions I want you to write down in your science journal, and I want you to answer them from the information we just talked about. Okay? If you need to, pause it. Pause this information and write it down and then answer the question. Or if you have to, go back and listen to what we talked about and then write your answer. Okay? Okay, now we're going to talk about tools and accuracy. Tools and accuracy. So we're going to use this information as an example. Okay? If you'll notice, we have a flask and a graduated cylinder. Okay? No measuring tool provides a perfect measurement. All measurements have some degree of uncertainty. Okay, so I'm going to use this information here in front of you to show you how some pieces of equipment are more accurate than others. Okay, so some measuring tools are not as accurate as others as we talked about. So the flask that's right here, is divided into 25 milliliter increments. But believe it or not, it measures volume with less accuracy than the graduated cylinder right here, which is divided into 0.5 milliliter increments. The uncertainty in a measurement is a plus or a minus half of the smallest division. So in this case, for this flask right here, the increments right here is 25 milliliter. You take and you divide that in half, so the accuracy is plus or minus 12.5 milliliters for the flask. However, when you take a look right here at the graduated cylinder, the uncertainty of measure of the graduated cylinder is plus or minus 0.25 milliliters. Okay, 0.25 versus 12.5. Okay, so between these two, the more accurate measure comes from the smallest, which is the graduated cylinder. Okay, now we want to talk about scientific notation. Suppose you're writing a report that includes Earth's distance from the Sun, which is 149,600,000 kilometers, and the density of the Sun's lower atmosphere, which is 0.0000000028 grams per centimeter cubed. Now I know that's a lot, but I'm going to show you where it's at, so hold on just a second. Move that over there. I'm going to point so that you can see the information. Here was the first one I used, which is Earth's distance from the Sun. The second one, which is B, is the density of the Sun's lower atmosphere. Okay? Now, suppose you want to include those two things in your written report. Now, like me, saying all those zeros was kind of silly. Okay? So these numbers take up too much space in your report, so you need to use something called scientific notation. Now, here's what I want you to do. Scientific notation happens to be one of your vocabulary words. So if you could please write that word down, and also the definition that's beside it, which is a method of writing or displaying very small or very large numbers in a short form. Okay, write that in your science journal. Okay, and I'm going to talk a little bit more about it because we're going to try to convert some of these numbers so that it makes it a whole lot easier for you to use in your report. Okay, so going back to what I was saying, these two numbers, that one and that one, to write the numbers above in scientific notation, use the steps that I'm going to show you. Okay. And that is going to help you. Okay, so write your original numbers, which is what we did here. Okay, move the decimal point to the right or to the left to make the number between 1 and 10. Okay, count the number of decimal places moved and note the direction. So we're going to try this one right here. Okay, so we moved the decimal place from down here, right there, to over here, if you notice, in A, and we moved it 8 places to the left. So now it's 1.496, 0, 0, 0, 0, 0, which we've moved 8 places. Okay, let's do the same with the other one. Okay, B, we're looking at B. We're taking this number and we're moving our decimal place over from down here to down here, which was also 8 places, but it's to the right instead of the left. Okay, now, step number 3. You're going to rewrite the number, deleting all extra zeros to the right or to the left of the decimal point. Okay, so now if you take a look how many zeros we had right here, and we've deleted them at this point. There's no extra zeros. All right. Same with this number here. We've deleted all the extra zeros and come up with just the number and the decimal point. Okay, next. Write a multiplication symbol, okay, and the number 10 with an exponent. Now, the exponent should equal the number of places that you move the decimal point in step 2. That's this one here. If you move the decimal point to the left, the exponent is a positive. So which one did we look at that was a left? We moved it 8 places to the left. So your exponent is going to be a positive number. Okay, we moved 8 to the left. Okay. If you moved the decimal point to the right, the exponent is going to be negative. This one we happen to move 8 places to the right. So now, when you take a look at the information right here, A would be written like this: 1.496 times 10 to the 8th power. Okay? B would be 2.8 times 10 to the negative 8th power. Okay? So that's giving you an easier way to write the information. It still means the same as these things here, but takes up less space and easier to talk about. Okay? Okay, so now I want to take this information and make it smaller since we've talked about it. Okay? And I want to ask some questions. I want you to write these questions down in your science journal, and I want you to answer them. The first one would be this one. What is scientific notation? What is scientific notation? Okay. The next one would be this one here with the yellow key with the red check mark in it, which it's called a key concept, one of the things we want to master by the end of this lesson. Okay, so why is scientific notation a useful tool for scientists? Okay, the last one I want you to write down for right now would be this one. Earth's circumference is about 40 million meters. Write this in scientific notation. This information right here. Go back after you write this question and use that chart and go through each one of the steps to get your scientific notation written down. Okay. Next we're going to talk about percent error. I want you to recall back to that chart where the 3 students were testing the densities of sodium chloride. Okay? The densities recorded in that chart were experimental values because they were calculated during an experiment. Each of these values has some error because the accepted value of the table salt density was 21.65 grams per centimeters cubed. Percent error can help you to determine the size of your experimental error. So what I want you to do is, I have, guess what, another definition. Okay, because percent error happens to be one of the vocab words. So please write percent error in your vocabulary words in your science journal and write the definition is the expression of error as a percentage of the accepted value. Okay, so you might assume that every experiment produces accurate results, or that all the data obtained through experimentation is accurate. I want you to know, though, for a fact, that all data contains uncertainty or error. When performing an experiment, it is important to calculate the percentage of error. Okay, so now we're going to close this down and we're going to bring up the chart that's right here because it's quite important that we learn how to do this information, okay? Because I just now told you that you needed to calculate percent error with everything you do, okay? So we're using this as an example. Solve for percent error, as it says right here. A student in the laboratory measures the boiling point of water at 97.5 degrees Celsius. If the accepted value, remember accepted value would be the value that the scientists accept. Okay, the accepted value for the boiling point of water is 100 degrees Celsius. What is the percentage or the percent error? Okay, so we're going to follow the steps. Number 1, this is what you know. You've already been told that your experiment showed the value of 97.5 degrees Celsius, okay? But we know the accepted value is 100 degrees Celsius. So those are the two things that you know. Number two, this is what you need to find out. You need to find out the percent error. You're going to use this formula right here. Percent error equals your experimental value, which is 97.5, minus your accepted value, which was 100. You're dividing that by the accepted value, which is 100. Okay? And then you're multiplying it by 100%. All right? So number 4, substitute the known values in the equation and perform the calculations. So if you know percent error is equal to 97.5 minus 100, all of that divided by 100 times 100%, you're going to get 2.50%. All right, that is what your percent error would be in this experiment. Okay, so here's what you're going to do now. I want you to write this in your science journal. I want you to try this one. You're going to calculate the percent error. If the experimental value of the density of gold is 18.7 grams per cubic centimeter, and the accepted value is 19.3 grams per centimeter cubed. Okay, so all you're doing is taking these same steps right here, and you're applying this to it. Okay, and you're writing it in your science journal using these steps, and I want to see the steps, please. Okay, so this is going to be required for class, so please bring it to class. Okay, so the last thing I want you to do, now that you've done that exercise, I want you to write these questions down in your journal and answer them. Okay? Why calculate the percent error in an experiment? That's one question. I want you to write it down and I want you to answer it from the information we just talked about. Okay, the last question I want you to answer is this one. Write it down and answer it in your journal. What conclusion can you draw if your percent error is high? Okay, those two questions, I want you to write down and answer them in your science journal. Okay, so now we want to talk about scientific tools. As you conduct scientific investigations, you will use tools to make measurements. The tools listed here, or the tools that I'm going to show you, are some of the tools commonly used in science. Okay, not all of them, but commonly used ones, things that you're going to probably see as we go through this year in science. Okay, so one of them is the science journal. Okay, we're going to use the science journal a lot for writing data and information and questions and answers so that I can see that you're doing what you need to do and give you some immediate feedback on that. Okay, so that's one tool that we use in science. Another one is balances. Okay, a balance is used to measure the mass of an object. Units often used for mass are kilogram, gram, milligrams, and a couple of others. But those three are the most common ones we use. Two common types of balances are the electronic balance and the triple beam balance, which I'm showing you right here. This is a triple beam balance. In order to get the most accurate measurements when using a balance, it is important to calibrate the balance often. Those will be done for you. You won't have to do that, but it's just a measure we take to make sure that the weights are correct so that we get the right measurements. Okay, so the next scientific tool I want to show you is glassware. Laboratory glassware is used to hold or measure the volume of liquids. Flasks, beakers, test tubes, graduated cylinders are just some of the different types of glassware available. Volume usually is measured in liters and milliliters. The next one I want to show you happens to be something that we will be using for a fact, and that is thermometers, which is right here measuring the temperature of this liquid. A thermometer is used to measure the temperature of substances. Although Kelvin is the SI unit of measurement for temperature, in the science classroom you often measure temperature in degrees Celsius, which is degrees with a C. Never stir a substance with a thermometer because it might break. If a thermometer does break, tell your teacher immediately. Do not touch the broken glass or the liquid inside the thermometer. Okay, so the next scientific equipment I want to show you is something that you guys are very familiar with, and that is the calculator. A handheld calculator is a scientific tool that you might use in math class, but you also can use it in the lab and in the field to make quick calculations using the data that you've found. Okay, the last one I want to show you would be this. It is a computer. Okay? For today's students, it is difficult to think of a time when scientists or anyone did not use computer in their work. Scientists can collect, compile, and analyze data more quickly using a computer. Scientists use computers to prepare research reports and to share their data and ideas with investigators worldwide. Hardware refers to the physical component of a computer, such as the monitor and the mouse. Computer software refers to the programs that are run on the computer, such as word processing, spreadsheet, and presentation programs. Electronic probes can be attached to computers and handheld calculators to record measurements. There are probes for calculating different kinds of information, such as temperature and also speed of an object. Okay, so these are just some scientific tools that we could use or will be using. Okay, now I want to ask some pertinent questions, so make sure you've got your science journal out and you're writing these questions down and answering them. Okay, this first one, what do thermometers measure? The second, what kind of experiment might use a thermometer? Okay, and the last one I want to ask you about that is, what could measuring the temperature of a substance tell you? Alrighty. Ready for some more? Okay, we're going to ask this question too. Write these down. If you need to, remember you can pause this, write your question and answer them, and then continue on. Next question. Why are calculators used in labs? Alright, dealing with the calculator. Okay, another one. What are some calculations you might need to make in science experiments? That's this one right here. Please write those down. Answer those questions. Okay, so the last three that I want to ask you. How do scientists use computers in a lab? How about the next one, which is the gold key with the red check mark, which means it's a key concept question? How can scientific tools such as graduated cylinders and triple beam balances assist physical scientists? Okay. The last one here that I want you to write down and answer is, why would you want to record the results of your investigation on a computer? Okay, that's this one. Okay, so some of the last information that I want to provide to you, you make sure you've written down all of these questions and answered them, please. Okay, so the last of the information I want to provide you is some additional tools used by physical scientists. And I'm just going to make these a bit larger. Okay, you may know what some of them are, and then again, you may not know what some of them are. Okay, so this first one right here pH paper. You can use pH paper to quickly estimate the acidity of a liquid substance. The paper changes color when it comes in contact with an acid or a base. Okay, this one right here is a hot plate. And a hot plate is a small heating device that can be placed on a table or a desk. Hot plates are used to heat substances in the laboratory. Okay, the next one is this right here. I think you probably know what that one is. Scientists use stopwatches to measure the time it takes for an event to occur. The SI unit for time is seconds. However, for longer events, the units, minutes, and hours can be used. Okay, the last one is this right here, and it is a spring scale. You use a spring scale to measure the weight of the amount of force applied to an object. The SI unit for weight is in newtons. Okay, I want to ask you one last question. All right, I want you to write this in your science journal, and I would like for you to actually answer this one, and that is, oops, let's move some of this up so we have a spot. How are spring scales, pH paper, stopwatches, and hot plates used in physical science investigations? How would you use these last few items that I showed you here as a physical scientist in your investigation? Okay, so I want that answered also, please. If you need to, make sure that you're stopping this, writing your information, and then coming back and starting it up again to finish the program. Okay, so now we come to the lesson review. All right, I want you to read the questions, and I want you to write your answers only. You do not have to write the question, just the answers. Okay, but I do want you in your science journal to do this graphic organizer and answer it. So I want the graphic organizer there as well as your answers for that. Also, please make sure that you're doing your math skills and doing the calculations and showing me the steps, please. I want to see the steps for this math skills exercise. Okay? I will be reviewing all that information with you. Remember, if you have questions on any of this information, you may stop this, replay it at any time to go back through the information. If at some point you still don't understand some of the information, then please write down your question for me so that we can discuss it and clarify it for you. You can do this by talking to me in class, or you may bring it to me at lunchtime or after school when my door is always open for you students. Thank you. I hope you've learned a lot in this lesson.